In 1977, we launched a spacecraft designed for a 4-year mission. It's still transmitting. Voyager 1 is now more than 24 billion kilometers from Earth. That's not a typo. 24 billion. The most distant human-made object in the history of our species. And in 2012, 35 years after launch, on a mission that was supposed to end before 1982, it crossed into interstellar space. It left the solar system. And what it found when it got there wasn't what anyone fully expected. I'm Paul Dirac. Let's talk about what Voyager actually did, what it actually measured, and what the data actually means, because the headlines don't do it justice. Start with how it got there. Voyager 1 didn't carry enough fuel to reach interstellar space under its own power. No spacecraft we could realistically build could. The distance is too vast. The energy required would be prohibitive. So instead, mission planners used something far more elegant, the planets themselves. Gravitational assist. Each time Voyager flew past a massive planet, Jupiter, then Saturn, it fell into the planet's gravitational field, curved around it, and exited on the other side with more speed than it entered. Not because the planet gave it fuel, it didn't, but because the probe borrowed momentum from the planet's orbital motion. The planet slowed by an immeasurably tiny amount. Conservation of momentum is satisfied. The probe accelerates. Free velocity paid for with nothing but careful mathematics. The trajectory that made Voyager possible, the grand tour of the outer solar system, exploited a rare planetary alignment that occurs once every 175 years. Jupiter, Saturn, Uranus, and Neptune in positions that allowed a single spacecraft to visit all four, using each for a gravitational assist to reach the next. A 25-year-old engineer at JPL named Gary Flandreau identified this alignment in 1965. Without that calculation, without that window, which opened in 1977, and wouldn't return until 2153, Voyager as we know it doesn't exist. Physics built the mission, mathematics found the window, and a young engineer with a pencil and orbital mechanics made it real. Now, where does the solar system actually end? Most people think Pluto or Neptune, or some vague region past the outer planets. This is wrong. Not approximately wrong, but wrong in a way that reveals something important about what the solar system is. The sun doesn't just emit light, it continuously emits matter, a stream of charged particles, primarily protons and electrons, flowing outward at 400 to 800 kilometers per second in every direction. This is the solar wind. It doesn't stop at Neptune. It doesn't stop at Pluto. It keeps flowing outward until it runs into something strong enough to push back, the interstellar medium, the thin gas and magnetic field that fills the space between stars. The region dominated by the solar wind is called the heliosphere. Think of it as a vast bubble, the sun's domain, defined not by distance but by influence. At some distance from the sun, the solar wind pressure equals the pressure of the interstellar medium. That boundary is the heliopause. Beyond it, interstellar space. Inside it, the sun's territory. The heliopause isn't at a fixed distance in all directions. The sun is moving through the galaxy, orbiting the galactic center at about 220 kilometers per second, and this motion compresses the heliosphere in the direction of travel and stretches it in the trailing direction. It's not a perfect sphere. It's asymmetric, dynamic, shaped by the sun's motion and the density of the surrounding interstellar medium. Voyager 1 crossed the Heliopause in August 2012. At a distance of about 121 astronomical units from the Sun, 121 times the Earth-Sun distance. That's where the solar system ends, in the physically meaningful sense, where the Sun's wind stops. And what happened at that crossing was not what scientists expected. As Voyager approached the heliopause, it entered a region called the heliosheath, the compressed, turbulent zone where the solar wind had slowed from supersonic to subsonic speeds, heated by the collision with the interstellar medium. This region behaved strangely. The magnetic field fluctuated. Particle fluxes varied unexpectedly. The boundary showed up not as a single crossing, but as a series of partial crossings. Voyager appeared to briefly exit and re-enter the heliosphere multiple times before the final definitive crossing. The heliopause was not a clean wall. It was a turbulent, contested frontier. The definitive signal of the crossing, a sudden dramatic drop in solar wind particles, the charged particles streaming from the Sun, and a simultaneous sharp increase in galactic cosmic rays. Cosmic rays are high-energy particles, protons and heavier nuclei, accelerated by supernovae and other violent events in the galaxy, streaming through interstellar space from all directions. Inside the heliosphere, the solar wind deflects and reduces them. Outside, they're present at full galactic intensity. When Voyager's instruments registered this transition, the case was complete. It was in interstellar space. The magnetic field changed direction too. Inside the heliosphere, the field was oriented along the Sun's own magnetic field structure. Outside, it aligned with the local interstellar magnetic field, a different direction, a different origin, a field threading through the galaxy rather than the solar system. Two magnetic environments meeting at a boundary Voyager crossed in real time, its instruments recording the transition. Now, what is interstellar space actually like? Because here's where most people's intuition fails. It's not empty, not even close, by the standards of what empty typically implies. The interstellar medium is a diffuse plasma, ionized gas, mostly hydrogen and helium, at extraordinary low density, roughly 0.1 atoms per cubic centimeter in the region Voyager now traverses. For comparison, Earth's atmosphere at sea level contains about 27 million trillion molecules per cubic centimeter. Interstellar space is genuinely thin by any practical measure, but it's not vacuum. It has structure. It carries magnetic fields. It carries cosmic rays streaming at significant fractions of the speed of light. It has temperature. The local interstellar medium near the Sun runs at about 6,000 to 10,000 Kelvin in terms of particle kinetic energy, though the density is so low that this temperature wouldn't feel warm to any instrument in the ordinary sense. Everything we knew about the local interstellar medium before Voyager was inferred, deduced from observations made from inside the heliosphere, filtered through the very bubble we were trying to see beyond. Voyager gave us the first direct in situ measurements, actual particle counts, actual magnetic field readings, actual cosmic ray fluxes, unshielded and unfiltered by the solar wind. The data is irreplaceable in a way that no telescope observation, however sophisticated, could replicate. Now let me tell you something about the engineering that will, I think, change how you feel about the mission. Voyager 1 communicates with Earth using a 22-watt radio transmitter, 22 watts, roughly the power of a refrigerator light bulb. That signal travels at the speed of light, the fastest anything can travel, and takes more than 22 hours to reach Earth. When you send a command to Voyager, you wait 44 hours for a round trip. The signal that arrives after crossing 24 billion kilometers is so faint that receiving it requires the enormous dish antennas of NASA's Deep Space Network, and the power received is roughly 1 part in 10 to the 22nd power of what was transmitted. We are detecting the electromagnetic equivalent of a whisper from beyond the solar system. The power source is 3 radioisotope thermoelectric generators, RTGs, fueled by the radioactive decay of plutonium-238. No solar panels could work at this distance. Sunlight is too faint. The plutonium decays steadily, generating heat, which the RTGs convert to electricity. Power output decreases by about 4 watts per year. Over decades, instruments have been shut down one by one to conserve power for the few remaining operational sensors. Scientists estimate that Voyager 1 will maintain enough power to transmit until somewhere between 2025 and 2036, at which point the signal stops and the spacecraft continues in silence. After that, it doesn't stop moving. There's nothing to stop it. No friction, no air resistance, no significant gravitational force to slow it meaningfully. It continues on its current trajectory forever, or until it encounters something which on the timescales of interstellar travel is almost vanishingly unlikely. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light years of the star Gliese 445. Not close enough to be captured, just passing through the neighborhood. Voyager carries a message, a 12-inch gold-plated copper disc, the Golden Record, containing sounds and images selected to represent life on Earth. Music from 27 cultures, greetings in 55 languages, sounds of wind, rain, surf, thunder, birds, whales, brain waves of a young woman in love, 116 images including a nursing mother, DNA structure, human anatomy, and scenes of daily life across the planet. The instructions for playing the record are encoded on its surface in a form intended to be decipherable by any intelligence capable of intercepting a spacecraft in interstellar space. It was assembled under Carl Sagan's direction, and it was sent not because anyone expects it to be found. The odds are essentially 0 on any human timescale, but because the act of sending it said something about us, that we wanted to be known, that we thought, across a silence we had no reason to believe would ever be broken, that something might be listening. I find that worth noting. Now, what we don't know, because honesty requires this. Voyager's data raised questions it couldn't answer. The shape of the heliosphere, long assumed to be comet-shaped, compressed in the direction of solar motion and trailing a long tail behind, is now actively debated. Some analyses of Voyager's measurements and data from the IBEX mission suggest the heliosphere may be nearly spherical, without the predicted tail. The structure of the heliopause remains incompletely characterized. And beyond Voyager's current position lies the Oort Cloud, a vast hypothetical shell of icy bodies extending perhaps a quarter of the way to the nearest star, the reservoir of long-period comets. Hypothetical because it has never been directly observed. Voyager won't reach it for thousands of years and won't have functioning instruments when it does. The outer solar system, in this sense, remains unmapped. And then the pale blue dot. In 1990, at Carl Sagan's request, Voyager 1 turned its camera backward, toward the inner solar system, toward Earth. At that distance, Earth appeared as a fraction of a pixel, a pale blue dot suspended in a band of scattered sunlight. Every person who ever lived on that dot. Every love, every war, every work of art, every atrocity, every moment of beauty or terror or genius, all of it on a speck of dust suspended in a sunbeam. Voyager didn't just cross the heliopause, it gave us a scale. It demonstrated concretely, with data and distance and a photograph, that we live on a small planet circling an ordinary star on the outskirts of a galaxy of 400 billion stars in a universe of at least 2 trillion galaxies, not as a poetic sentiment, as a measured fact. The probe is still moving. It will never stop. Long after every institution that built it has dissolved, long after the civilization that conceived it is gone, Voyager 1 will continue outward, carrying a record of who we were, into a silence so vast that the word vast doesn't reach it. A message in a bottle, thrown into an ocean with no shore. That's what the data shows. That's what the mission was. And I think it's one of the most remarkable things our species has ever done.